The variable capacitance DP transducer is a very popular device which is used to sense and transmit pressure differences. People often face issues with the sluggishness and fast response of these instruments. In this particular video, we are going to deep dive into working of these DP cells, prepare mathematical model, and then give you a practical guidance how to improve the response of the DP transmitter or pressure transmitter. Now, in this particular picture, you can see that there is a pressure transmitter, or you can say this is a DP transmitter. If it is only pressure transmitter, there will be only one side this diaphragm is present, other side there is no diaphragm. Now these are the external diaphragm which are directly connected to the process, and the pressure is exerted on the external diaphragm. It gets transmitted through the capillary tube and falls on the isolating diaphragm. So this is the inner portion picture here, and this can be further enlarged into this picture. So pressure is first exerted on the isolating diaphragm. It transmits through the capillary and goes into the isolating diaphragm. Now isolating diaphragm is inside the transmitter and it is sealed. Now when the pressure is falls on this isolating diaphragm, this pressure is transmitted through the field fluid within the pressure capsule, and ultimately pressure gets exerted on the sensing diaphragm. On the both sides of sensing diaphragm there are capacitor plates. Now as pressure is applied, the distance between the capacitor plate and the sensing diaphragm changes, and this change in capacitance is measured through electronic circuit. In the case of only pressure transmitter, pressure is exerted from one side. In the case of the DP transmitter, this pressure is exerted from the both side of the isolating diaphragm. In the case of the DP transmitter, one side of the isolating diaphragm is facing a pressure P1, another side is P2. So the force that is exerted inside the capsule is P1A minus P2A, considering P2 is less than P1. Now this force will be equal to the mass and acceleration of the capsule from the Newton's second law of Newton. Further, this pressure P2A is equal to the resistance exerted by the diaphragm plus the viscous force exercised by the liquid. Now, if K is the Hooke's constant and C is the damping coefficient, then this P2A will be equal to Kx plus C dx dt, right? So, this we can put here, this formula. Then what will happen? Then P1A will become P2A plus this portion. Now P2A already we are saying Kx plus C dx dt, right? And it will plus with the, this is the mass portion, this is the mass, right? Where A is the cross sectional area, L in the length, rho is the density, and divided by Gc is your gravitational coefficient for acceleration into d2x into d22, right? So this is what we get. Now you can further divide whole by A, and uh, and then you do the Fourier transform. After you do the Fourier transform, you will get a equation like this, where it will be Kp divided by 1 plus K1s and then K2 square. So this K1 and K2 are some constant based on all these constants are there based on some constant. But my purpose of showing this here is you can see the response. So this is the response, right? Response of the capsule when some pressure is exerted onto it. And this response is a second order response. Means whenever there is a change in pressure, the displacement of the sensing diaphragm will follow this pattern. And if this pattern is followed, the same will be followed in the current output of the transmitter, right? So this can be difficult to measure sometimes, because if it oscillates so much, it will be difficult to measure and you will be getting the fluctuating readings. That's why it is very important to properly tune your transmitter. And most of the manufacturer in nowadays with the electronics transmitter does it very efficiently, and you hardly see this kind of variation, so much variation in the output. But if it is there, you need to really see into the parameters that you can change within the transmitter and tune your pressure transmitter or DP transmitter properly. So if you see, this is an example, this is an Rosemount 3051 transmitter, and if you go into the manual, there is one particular coefficient called damping, and this particular damping parameter can be changed through hard communicator or through other configurators, right? And this damping parameter can be set within a range of 0 to 60 degrees. In the factory, Emerson sets the output of the Rosemount 3051 CD at 3.2. But if the transmitter output is still noisy, increase the damping time. If you need a faster response, decrease the damping time. So if you want a sluggish response or it is very, very noisy, in that case, you need to increase the damping. But if you want faster output, you need to decrease the damping coefficient, right? But as a default, it is normally set at 3.2 and the range is 0 to 60 seconds. Hope you got a clear idea how a DP transmitter or pressure transmitter responds to a pressure change and how you can adjust that. Thank you.